Hello, everyone, and welcome to my mini lecture. Today, we will explore together the different types of industrial light sources and their performance parameters. In machine vision, while the industrial camera is the eye capturing the world, the light source serves as the lighting technician that reveals even the smallest details. Now, let us enter the lecture to see how they illuminate our production path and improve both efficiency and quality. This lesson will primarily cover the following 3 topics. It is hoped that through this lesson, you will achieve the following objectives. First, let us understand what an industrial light source is. Through proper illumination design, it can effectively separate the target information from the background. This greatly reduces the complexity of image processing algorithms, improves the system's positioning and measurement accuracy, and enhances the system's reliability and overall robustness. Conversely, if the light source selection and illumination design are not appropriate, the design of image processing algorithms and imaging systems will become significantly more challenging and inefficient. The roles of an industrial light source in a machine vision system include 1. Illuminating the target to create favorable imaging conditions. 2. Overcoming external light interference to ensure the stability of system imaging. 3. Emphasizing the features on the target that need processing while suppressing unwanted features, thereby simplifying the image processing algorithms. Next, let us explore the classification of industrial light sources. Industrial light sources come in various forms and types, and are typically classified according to luminous material, light wave characteristics, and shape or structure. Number 1. Classification by luminous material. LED light sources. Characterized by energy efficiency, long service life, high speed response, easily adjustable brightness, and readily available emission colors. Halogen light sources. Characterized by low cost, compact size, high heat generation, high operating temperature, and an inability to be switched on and off frequently. Fluorescent light sources. Characterized by rapid aging, with brightness quickly diminishing over time, and are now rarely used as industrial light sources. Xenon light sources. Characterized by consistent electrical parameters, minimal influence from external conditions on their operating state, high light intensity, and the ability for continuous rapid illumination. Laser light sources. Characterized by uniform illumination, a broad spectral range, high light intensity, good stability, and long service life, although their manufacturing cost is relatively high. Number 2. Classification by light wave characteristics. White light sources, usually defined by color temperature. White light sources with a color temperature above 5000 K tend to appear slightly blue. Those below 3300 K tend to appear slightly red, and those between 3300 K and 5000 K are considered neutral. White light sources are widely applicable and highly bright, especially when capturing color images. Blue light sources, with a wavelength range between 435 nanometers and 480 nanometers. They are widely used for inspecting metal products, such as railway tracks, cold-rolled steel strips, ship components, and mobile phone casings. Red light sources. Typically with a wavelength between 605 nanometers and 700 nanometers, their longer wavelength allows them to penetrate darker objects. For example, They are useful for positioning through holes in black, transparent, flexible boards, for green circuit board trace inspection, or for measuring the thickness of translucent films. Using red light sources can enhance contrast. Green light sources. With a wavelength range of 500 nanometers to 560 nanometers, they fall between red and blue and are mainly used for products with red or silver backgrounds, such as sheet metal or machine parts. Infrared light sources. Typically with a wavelength between 750 nanometers and 1000 nanometers. They are invisible and have strong penetrative ability. Infrared light sources are commonly used in LCD screen inspection and video surveillance applications. Ultraviolet light sources. With wavelengths generally between 10 nanometers and 400 nanometers. They have short wavelengths and strong penetration, and are mainly applied in areas such as document inspection, touch screen conductive glass detection, fabric surface damage detection, adhesive overflow detection, and metal surface scratch inspection. In addition to wavelength, light also possesses hue characteristics. In optics, if two colored lights are mixed in appropriate proportions to produce white light, these two colors are called complementary colors. When complementary colors appear together in an image, they evoke a stronger visual contrast, making reds appear redder and greens appear greener. By extracting the characteristic color of a product and selecting a light source that is complementary to that color, the contrast between the product's features and the background can be enhanced, thereby accentuating those features. Conversely, using a light source that is the same as or similar to the background color can effectively reduce background interference with feature extraction. When the image acquisition device is a monochrome camera, a light source close to the background color can be used to reduce background brightness, or one significantly different from the background color can be used to increase background brightness. For example, when the background is red, if one wishes to emphasize the difference between defects and the background, in a bright field one can select a purplish red or orange light source that is close to red, whereas in a dark field one should choose a cyan light source that differs significantly from red. The fundamental purpose of choosing the light source color is to enhance the contrast between the object's surface features to be inspected and the background. Number 3. Classification by light source shape. 1. Ring light sources. Suitable for highlighting the edge features of an object and features with certain height variations. 2. Bar light sources. With flexible length options, they are suitable for detecting defects in product appearance and for image scanning. 3. Spot light sources. Suitable for inspecting relatively small objects. 4. Planar light sources. Provide overall uniform illumination by eliminating shadows and reflections through even lighting. They are further divided into front light sources and backlight sources. 5. Coaxial light sources. With a diffusing plate in front of the light source, they can eliminate ghost images in captured images and provide excellent uniformity. 6. Dome light sources. Suitable for inspecting curved surfaces, uneven surfaces, or arc-shaped surfaces, as well as objects with strong reflective properties on metal or glass surfaces. Having understood the diverse classifications of industrial light sources, let us now delve into the different illumination methods to see how they function in practical applications. There are primarily 6 illumination methods. One. Vertical illumination. This is where the light source is directly below the camera, with the target object positioned directly beneath the light source. Vertical illumination can highlight detailed surface features of a product, but it is prone to interference from surface characteristics. 2. High-angle illumination. This refers to a ring light source with an incidence angle between 45 degrees and 90 degrees. High-angle illumination, with its relatively large distance, can illuminate smooth surface features. 3. Low-angle illumination. This refers to a ring light source with an incidence angle of less than 45 degrees. With a lower angle, it can illuminate surface features with height variations, causing a smooth surface to appear darker. 4. Back illumination. This method makes the measured object appear darker while the background becomes brighter, thereby emphasizing the outer contour of the object. It is suitable for high-precision dimensional measurement, contour positioning, and edge defect detection. 5. Coaxial illumination. Light from the LED is diffusely projected onto a semi-transparent, semi-reflective beam splitter and then reflected onto the object's surface. When the object's surface receives the light, it reflects it back onto the beam splitter, which directs it into the camera. This method can darken features with a certain height while brightening flat surfaces. 6. Hemispherical integrating illumination. Densely arranged LEDs on a circular circuit board, combined with a special coating inside the sphere, cause the LED light to be uniformly and smoothly diffused onto the surface of the object. This method is suitable for inspecting objects with uneven or highly reflective surfaces. Everyone, this mini lecture on types and performance parameters of industrial light sources comes to an end. It is hoped that you will apply the knowledge learned in this lesson to your practical work, continually enhancing product quality with a commitment to excellence. See you in the next lesson.